Okay, last chapter of the semester, chi-square and F distributions. Chi-square test of independence and of homogeneity. All right, go ahead and take a look at your focus points. Write them down if that's what you do. All right, Innovative Machines Incorporated has developed two new letter arrangements for computer keyboards. The company wishes to see if there's any relationship between the arrangement of letters on the keyboard and the number of hours it takes a new typing student to learn or type at 20 words per minute. Or from another point of view, is the time it takes a student to learn to type independent of the arrangement of the letters on a keyboard. To answer questions of this type, we test the hypotheses. H sub 0 keyboard management and learning times are independent, or H sub 1 keyboard arrangement and learning times are not independent. In problems of this sort, we are testing the independence of two factors. The probability distribution we use to make the decision is the chi-square distribution. As you know from the overview of the chi-square distribution, that chi is pronounced like the first two letters of the word kite and is a Greek letter denoted by the symbol. Thus, chi-squared is denoted by that. And they're actually writing it wrong because they're writing the X up higher. In Innovative Machines' first task is to gather data. Suppose the company took a random sample of 300 beginning typing students and randomly assigned them to learn on type 1 to type on one of the three keyboards. The learning times for these samples are shown in table 10.2. Okay, these learning times are the observed frequencies O. The table 10.2 is called the contingency table. The shaded boxes that contain observed frequencies are called cells. The row and column totals are not considered to be cells. This contingency table is a size 3 by 3 because there are 3 rows of cells and 3 columns. When giving the size of a contingency table, we always list the number of rows first. To determine the size of the contingency table, count the number of rows containing data and the number of columns containing data. The size is number of rows times number of columns, where the time symbol is read by the number of rows is always given first. We are testing the null hypothesis that the keyboard arrangement and the time it takes a student to learn to type are independent. We use this hypothesis to determine the expected frequency of each cell. For instance, to compute the expected frequency of cell 1 in table 10.2, we observe the cell 1 consists of all the students in the sample who learned to type on keyboard A and who mastered the skill at 20 words per minute level in 21 to 40 hours. By the assumption null hypothesis that the two events are independent, we use the multiplication law to obtain the probability that a student is in cell 1. Probability cell 1 equals P equals the probability of keyboard A and skill in 21 to 40 hours. So probability of keyboard A times probability of skill in 21 to 40 hours. Because there are 300 students in the sample and 80 use keyboard A, be 80 over 300. Also, 90 of the 300 students learned to type in 20 to 21 hours. So that probability is 90 over 300. Using the two probabilities and the assumption of independence, we would have 80 over 300 times 90 over 300. Finally, because there are 300 students in the sample, we have the expected frequency E for cell 1. E equals the probability of student in cell 1 times the number of students in the sample. So 80 over 300 times 90 over 300 times 300 would be 24. We can repeat this process for each cell. However, the last step yields an easier formula for the expected frequency E. Formula for the expected frequency E is row total times column total over sample size. Okay, so 90, 150, 60, 80, 120, 100. Sample size is 300. So cell 2 is in row 1, column 2. The row total is 80 and the column total is 150 and the sample size is 300. So 80 times 150 over 300 equals 40. Now we are ready to compute the sample statistics chi-squared for typing students. The chi-squared value is a measure of the sum of differences between observed frequency O and the expected frequency E in each cell. Okay. So these differences are listed in table 10.4. You have your cell, your observed, your expected, your difference. All right. Take a look at that. As you can see, if we sum the differences between the observed frequencies and the expected frequencies of the cells, we get the value 0. This total certainly does not reflect the fact that there were differences between the observed and the expected frequencies. To obtain a measure whose sum does reflect the magnitude of the differences, we square the differences and work with the quantities observed minus expected squared. Each one. But instead of using the term, we use the values divided by the expected. Okay. We use this expression because a small difference between the observed and expected frequencies is not nearly as important as the expected frequency is large as it is when the expected frequency is small. For instance, for both cells 1 and 8, the squared difference is 1. However, this difference is more meaningful in cell 1, where the expected frequency is 24, than it is in cell 8, where the expected frequency is 50. When we divide the quantity observed minus expected squared by E, we take the same size of the difference with respect to the size of the expected value. We use the sum of these values to form a sample statistic chi-squared, where the sum is over all cells in the contingency table. Guided exercise 3. So we look at table 10-5. You guys are going to fill in the missing pieces. If I were you, I would just pause the video here and write everything out. So I will give you time to do that. Okay, so the last two rows of table 10.5 are then added into here. So the total of the last column, 13.31. Compute the chi-squared statistic for the sample. Okay. Notice that when the observed frequency and the expected frequency are very close, the quantity is close to 0. So the chi-squared is close to 0. As the differences increase, the chi-square also increases. To determine how large the sample statistic can be before we must reject the null hypothesis of independence, we must find the p-value of the statistic in the chi-square distribution, table 7 now of appendix 2, and compare it to the specified level of significance alpha. The p-value depends on the number of degrees of freedom. To test independence, the degrees of freedom are determined by the following formula. Go ahead and pause it so you can write that down. Let's determine the number of degrees of freedom in the keyboard example. As we know, the contingency table had 3 rows and 3 columns. Therefore, 3 minus 1 will give us 2. 3 minus 1 will give us 2. So the degrees of freedom are 4. To test the hypothesis that the letter arrangement on the keyboard and the time it takes to learn to type at 20 words per minute are independent at alpha equal to 0.05 level of significance, we estimate the p-value shown in figure 10.3 below for the sample statistic chi-squared to be equal to 13.31. So with degrees of freedom, you're between 0.010 and 0.005. We then compare the p-value to the specified level of significance alpha. For the test of independence, we always use a right-tailed test of the chi-square distribution. This is because we are testing to see if the chi-squared measure of the difference between the observed and the expected frequencies is too large to be due to chance alone. In guided exercise 4, we found the degrees of freedom to be 4. So then we see that it falls between 13.28 and 14.86. The corresponding p-values falls between 0.005 and 0.010. From technology, we get a p-value of about 0.0098. Since the p-value is less than the level of significance, we reject the null hypothesis of independence and conclude that keyboard arrangement and learning time are not independent. Test of independence for two statistical variables involve a number of steps. Summary of the procedure follows. Go ahead and pause the video so you can write this procedure down. Okay, go ahead and pause it here so you can write down the requirements. Remember, these are important when you go from question to question to see if it can actually fit into the type of problem set you're working on. All right, test of homogeneity. We've seen how to use contingency tables and the chi-square distribution to test for independence of two random variables. The same process enables us to determine whether several populations share the same proportions of distinct categories. Such a test is called a test of homogeneity. According to the dictionary, among the definitions of the word homogeneous are the same structure and composed of similar parts. In statistical jargon, this translates as a test of homogeneity to see if two or more populations share specified characteristics in the same proportions. Test of homogeneity tests the claim that different populations share the same proportions of specified characteristics. The computational processes for conducting tests of the same independence and test of homogeneity are the same. However, there are two main differences in the initial setup of the two types of tests, namely the sampling method and the hypotheses. Go ahead and read those for yourselves. Take note of what you need to take note of. All right, here's our next example. Pets can resist who can resist a cute kitten or puppy? Tim is doing a research project involving pet preferences among students at his college. Took random samples of 300 females and 250 male students. Each sample member responded to the survey question: if you could own your own pet, only one pet, what kind of pet would you choose? Possible responses were dog, cat, other pet, or no pet. The results of the study are in the table. Does the same proportion of males and females prefer each type of pet? Use a 1% level of significance. We'll answer this question in several steps. First, make a cluster bar graph showing the percentages of the females and the percentages of the males favoring each category of pet. From the graph, does it appear that the proportions are the same for males and females? So 40 compared to 54% for dog, 44 to 28 for cat, 6 to 8 to other, and 10 and 10 for no pet. So, we'll see what happens. Looking at the graph, it appears that there are differences in the proportions of females and males preferring each type of pet. However, let's conduct a statistical test to verify our visual impression. Is it appropriate to use a test of homogeneity? Yes, since there are separate random samples for each designated population, male and female. We also are interested in whether each population shares the same proportion of members favoring each category of pet. State the hypotheses and conclude the test by using the Minitab printout. Your null hypothesis: the proportions of families or females and males naming each pet preference are the same. Alternate: the proportions of females and males naming each pet preference are not the same. So here's your printout. Since the p-value is less than alpha, we reject the null at 1% level of significance. Okay. Interpret the results. It appears that the sample data that male and female students at Tim's college have different preferences when it comes to selecting a pet. Go ahead and pause the video for your procedure. It is important to observe that when we reject the null hypothesis in a test of homogeneity, we don't know which proportions differ among the populations. We know only that the populations differ in some of the proportions sharing a characteristic. Multinomial experiments, optional reading. We'll just kind of go through this and you guys can take note of it. And you might even want to pause the video here and do your homework and see if there's any questions related to it. Oops. Yeah, sorry. Just want to make sure that I get it all for you. Okay. All right, let's move on to section 10.2. All right, chi-square goodness of fit. Go ahead and read your focus points. All right, last year, the labor union bargaining agents listed 5 categories and asked each employee to mark the one most important to him or her. The categories and corresponding percentages of favorable responses are shown in 10.8. All right, vacation time, salary, safety regulations, health and retirement benefits, overtime policy and pay. You can see the favorable outcomes. The bargaining agents need to determine if the current distribution of responses fits last year's distribution or if it is different. In questions of this type, we are asking whether a population follows a specified distribution. And in other words, we are testing the hypotheses: the population fits the given distribution or the population has a different distribution. Okay. Next, we can use the chi-square distribution table to estimate the p-value of the sample chi-square statistic. Finally, we compare the p-value to the level of significance alpha and conclude the test. In the case of a goodness of fit test, we use the null hypothesis to compute the expected values of the categories. Let's look at the bargaining category problem to see how it's done. In the bargaining category problem, the 2 hypotheses are, you can read them for yourselves, I just read them. The null hypothesis tells us that the expected frequencies of the present response distribution should follow the percentage indicated in the last year's survey. To test this hypothesis, a random sample of 500 employees was taken. If the null hypothesis is true, then there should be 4% or 20 responses out of the 500 rating vacation time as the most important bargaining issue. So table 10.9 gives us the other expected values and all the information necessary to compute the chi-squared. Okay. We see that the sample statistic is 14.15. The larger values of the sample statistic indicate greater differences between the proposed distribution and the distribution followed by the sample. The larger the chi-squared statistic, the stronger the evidence to reject the null hypothesis that the population distribution fits the given distribution. Consequently, goodness of fit tests are always right-tailed tests. For goodness of fit test, we use the right-tailed test on the chi-squared distribution. This is because we are testing to see if chi-squared measure of the difference between the observed and expected frequencies is too large to be due to chance alone. To test the hypothesis that the present distribution of responses to bargaining categories is the same as last year's, we use the chi-square distribution, table 7 of appendix 2, to estimate the p-value of the sample statistic 14.15. To estimate the p-value, we need to know the number of degrees of freedom. In the case of goodness of fit test, the degrees of freedom are found by the following. So the number of categories minus 1. Suppose that when we compute the expected values E, we must use the null hypothesis to compute all but the last one. To compute the last one, we can subtract the previous expected values from the sample size. For instance, for the bargaining issues, we could have found the number of responses for overtime policy by adding the number of expected values and subtracting them from the sample size 500. We would again get an expected value of 30 responses. The degrees of freedom then is the number of expected values that must be computed by using the null hypothesis. For the bargaining issues, we have 4. We now have the tools necessary, table 7 of appendix 2, To estimate the p-value of chi-squared equal to 14.15, figure 10.5 shows the p-value. In table 7, we use the row headed by degrees of freedom equal to 4. We see that chi-squared 1415 falls between the entries 13.28 and 14.86. Therefore, the p-value falls between the corresponding right tail areas 0.005 and 0.010. Technology gives us a p-value of 0.0068. To test the hypothesis that the distribution of responses to bargaining issues is the same as last year's at 1% level of significance, we compare the p-value of the statistic to 0.01. We see that the p-value is less than alpha, so we reject the null hypothesis that the distribution of responses to bargaining issues is the same as last year's. At the 1% level of significance, we can say that the evidence supports the conclusion that this year's responses to issues are different from last year's. Goodness of fit tests involve several steps that can be summarized as follows. Go ahead and pause the video for your procedure. Go ahead and pause it for this part. All right, and this is the end of the first chapter coverage for chapter 10. We will have a second day for chapter 10. So please email me if you have any questions.